Look, if you're a procurement manager or a sourcing specialist, you already know the drill. Evaluating suppliers purely on that initial unit price, it's a trap. A really tempting trap, sure. Taking that 30% lower bid feels great in the moment. But let's be real. A part that's cheaper to cut right now, but ends up requiring hours of manual deburring or causes downstream welding failures, well, that's just not a bargain in the long run. Today, we're flipping the script and focusing entirely on your total cost of ownership.
Welcome to this explainer on the factors affecting laser cutting quality. We're going to completely unpack the exact technical specifications you need to be hunting for when auditing a supplier. And we aren't just nerding out on laser physics here. We're looking at how understanding these precise machine parameters will literally drive down your scrap rates, wipe out secondary processing costs, and get you that unmatched supplier reliability.
So here is our roadmap. We are going to look at finding hidden procurement costs, evaluating core hardware parameters, the trade-offs between speed and gas, material and machine stability, and wrap it all up with a zero-defect inspection checklist. All right, kicking things off with Section 1, Finding Hidden Procurement Costs.
You know how it is in industrial fabrication. Laser quality gets treated as subjective. Basically, hey, it looks fine on the pallet, right? But the reality is, quality is only subjective until it hits the final assembly line. That is exactly when the hidden costs rear their ugly heads. It's like an iceberg, right? And the biggest part under the water is the heat-affected zone, or HAZ. The HAZ is this area where excessive heat input literally alters the metal's edge metallurgy. And why should you care? Because if you're dealing with high-carbon steels, this intense heat can actually snap your drill bits if you try to tap holes later on. It warps thin parts, and it makes edges an absolute nightmare to weld. It's an invisible defect that triggers massive downstream labor costs.
Moving right along to Section 2, Evaluating Core Hardware Parameters.
Let's talk about the engine of the laser itself. When buyers look at a supplier's equipment on an RFQ, they usually just check the wattage and assume, hey, bigger number means better cuts. And sure, these modern fiber lasers exceeding 20 kilowatts, they are beasts. They redefine speed, cleanly slicing through 50 millimeters of stainless steel. But here's the catch. Raw power absolutely does not guarantee a superior finish. What really matters is beam stability. If a supplier boasts a massive 20 kilowatt laser, but the power source is aging or poorly maintained, you're gonna get power fluctuations. That ruins the consistency of your curve, and suddenly, your precision parts just don't fit together.
You also have to watch how that power is actually applied to the metal through the focal position. You've got to make sure your suppliers are using the exact right focus for your specific part. Take surface focus. It places the beam right on top of the material. This is ideal for thin stuff to keep a beautiful tight curve. But if you're cutting thick plates, they absolutely need to switch to negative focus, dropping that focal point down inside the material. Why? Because it helps the molten metal flow cleanly out the bottom. If they skip this, you get heavy dross, basically solidified slag. And guess what? Now you're paying someone an hourly wage just to stand there and manually grind it all off.
Okay, Section 3. This is absolutely crucial. Speed and gas trade-offs.
In the B2B world, we automatically equate speed with lower costs, right? Faster is cheaper. But in laser cutting, there is a very strict Goldilocks zone. Let's look at what happens when feed rates go wrong. Say your supplier rushes a job, cutting way too fast, just to maximize their own daily throughput. The laser literally doesn't have time to melt all the way through. The result? That awful heavy dross we just talked about, which instantly eats up whatever unit price savings you thought you were getting. On the flip side, if they cut too slow, the laser pumps way too much heat into the part. Your kerf gets wider, the heat-affected zone balloons out, and your thin parts end up warped and brittle.
Now, that feed rate has to balance perfectly with the most overlooked invisible quality factor in the game, assist gas. This right here dictates your secondary processing costs, so definitely pay attention to this part. Oxygen? It's cheap, but it leaves an oxidized, black, scaled edge. If you try to powder coat over an oxygen-cut edge, I guarantee that paint is going to peel right off. Nitrogen is pricier, but it leaves a perfectly clean, bright edge with zero oxide, which is absolutely mandatory if you're working with stainless steel, aluminum, or doing high-quality welding. And then there's compressed air. It's the cheapest of the bunch, but it leaves moderate carbonization. Honestly, it's only good for cost-sensitive internal parts that nobody's ever going to see. Bottom line, you have to specify the assist gas in every single contract.
Shifting gears now to Section 4, Material and Machine Stability.
So we've covered the laser beam and the gases, but what about the physical environment? The consistency of your raw material and the actual bed the machine sits on are incredibly vital.
Here are your sourcing baselines. First off, if you are sourcing reflective metals, think copper or brass, using older CO2 lasers is a disaster. They'll literally reflect the beam right back and destroy the optics. You must ensure the supplier uses modern fiber lasers. Second, surface contaminants like rust or oil totally mess with the laser's path. Top-tier suppliers use pickled and oiled, or P&O steel, to guarantee a smooth finish. And finally, motion control. If a supplier is running a lightweight, cheap machine frame, that thing is going to vibrate like crazy at high acceleration speeds. Those vibrations create visible vertical lines, called striations, right on the edge of your cut. Good factories know this, which is why they invest in heavy-duty cast iron or marble beds to completely dampen those vibrations. And that brings us to our final section, the Zero Defect Inspection Checklist. This is the actionable part. We're handing you the ultimate first article inspection tool to hold your supplier's feet to the fire. Next time you get a sample, run it against this rapid-fire audit. Do you see hardened dross attached to the bottom? They messed up the cutting speed. Is the edge tapered instead of perfectly square? They used the wrong focal position, seeing deep vertical striations. Their machine bed is vibrating. Notice significant discoloration from the heat-affected zone. They cooked the material by cutting way too slowly. And if your tabs and holes just flat out don't fit, their beam stability is terrible. Every single physical defect traces directly back to a technical variable they failed to control.
Let's tackle a real-world pain point, something we hear from buyers constantly. Why does my premium stainless steel have a weird yellow or brown edge? You're paying top dollar for this premium material, and it shows up looking burnt. What's going on there?
Well, here's the insider secret. That yellow or brown edge, it isn't a defect in the metal at all. It's a gas defect. It's caused by insufficient nitrogen purity, specifically anything less than 99.99% pure, or even just a tiny microscopic leak in the supplier's gas line that lets a little bit of oxygen slip in. If you are sourcing for medical or food-grade applications, your big takeaway here is to explicitly write high-purity nitrogen in your next RFQ. Don't leave it up to chance.
Let's look at one more super practical FAQ. How does a damaged nozzle affect my laser cut parts? This perfectly highlights why checking up on a supplier's maintenance schedule is so critical. Because frankly, it doesn't matter if they just bought $1 million machine if they aren't taking care of it. The nozzle's entire job is to direct that assist gas we talked about. If even a tiny metal clipping gets stuck inside it, or the nozzle gets dinged during a collision, the gas flow instantly becomes turbulent. And the result? You get an asymmetrical cut. One side of your part looks brilliantly smooth and perfect, while the adjacent side looks completely rough and jagged. All that high wattage means absolutely nothing without strict daily maintenance. Which leaves us with one final critical question for you to ponder. Are your current suppliers actually cutting costs, or are they just cutting corners? As we've seen today, real cost reduction comes from strictly controlling these technical variables, the gas purity, the focal length, the machine stability. It does not come from a supplier just cranking up the feed rate and passing the headache of deburring labor onto you. Take this checklist, reevaluate your supply chain, and start demanding a better total cost of ownership. Thanks for joining me on this deep dive, and seriously, go check those specs today.